Hello class, this is section 5.1 and today we will be learning about inverse functions. So before I begin defining an inverse function, we will start with an inverse relation. Now remember, a relation is similar to a function, but it's weaker than a function. A relation, you can have one input that gives you two outputs, right? So if you want to review that, you can go back to chapter 1 and review relations and functions. Anyways, an inverse relation is the following. Well, say you have a set. If you have a set of ordered pairs, and what is an ordered pair, you may be asking. I will give you a quick example. So say you have some set, and inside you have A, B, C, D. So an ordered pair is sort of like a point on a plane. You could interpret it like that. So that's an example of a set with two ordered pairs. Just one example. So if you have an ordered pair, interchanging the coordinates of this ordered pair produces the inverse relation. So let me write that down. Interchanging the coordinates of the pairs produces an inverse relation. So, for example, we had this set. If we just swap the pairs, we would get the inverse relation. So we could have the inverse of the above set would be BA and DC. And so that's what we mean by interchanging the coordinates. Just swap the A and the B, and we swap the C and the D. So this set is the inverse of this set. Now, there is other ways of representing a relation. If you review the chapter 1 stuff, you may remember we could use an equation or a formula to represent a relation. So if we have an equation with x's and y's in it, an equation or a relation with x's and y's in it, then interchanging the x's and the y's gives you the inverse relation. Interchanging the x and the y, or inverting the x and the y, gives an inverse relation. So a quick example of this, I don't know, say we have y equals x plus 2. Then the inverse relation of this, you just swap the y with an x and swap the x with a y. Right, so I swapped this with an x, I swapped this with a y, and that gives us the inverse version of that relation. Okay? So that's sort of two ways of thinking about inverse relations. Let me maybe do a few more examples here. Oops. So say we have the set of ordered pairs 3, -8, 6, 7, -2, -4. And we are asked to find the inverse. Okay. Well, this is pretty easy. We just swap the inputs and the outputs, or swap the coordinates. Swap the x's and the y's. So then we do -8, 3. Right, we just swapped. And then we do 7, 6, and -4, -2. Right, we are just swapping these, the x and the y. Swap the x and y values. Okay, now, when you look at this definition, we were not being very precise. Here we were saying if we have an equation with an x and y in it, we just swap the x and the y and we get the inverse. And that's true, but we should note that not every equation has an inverse. There is a condition we need to satisfy for an inverse to exist. And that condition is called a one-to-one condition. So we're now going to talk strictly just about functions and not relations. Let me first talk about one-to-one functions. Or I think in your textbook we use 1-to-1 in words. One-to-one functions. A lot of mathematicians just write this 1-1 as a shorthand for one-to-one. And I'll give you the definition of it, but it's a little mathy. If you don't understand the definition, I will give you an easier way to interpret the definition. So, a function f is one-to-one. What that means is that if some inputs, a and b, a does not equal b, if we have some inputs, two distinct inputs that do not equal each other, then f of a does not equal f of b. Okay, there's an equivalent way of writing this. An equivalent way of writing this is if the outputs equal each other, then the inputs must equal each other. Okay, so if you're having a hard time interpreting what this means, let me just draw some pictures here, and it will hopefully clear things up. So I'm going to draw some pictures on the XY plane. Maybe I'll draw 2 or 3. I'll do 4 pictures here. So here in green, I'll do a picture of a function. And I'll do a function here in red. Function in green. Function in red. Okay, now let's look at this green function. Say we look at this output. Say this is a, then this will be f of a. So if we look at this, if we have two outputs that equal each other on this green graph here, if f of a equals f of b on this green graph, we're left with no other choice but a equaling b, right? Because no matter what the other output is, if the inputs are different, the outputs will always be different, right? So this graph actually does satisfy the definition. So this this guy here in green as 1 to 1. Let's look at this graph in red. Let's say this is A, so that's f of A. Let's say this point here is B, so this is f of B. So in this particular situation, we have f of A equals f of B, but we also have A and B are different. So it fails this condition, right? We have two inputs giving the same output. So this graph here in red is not 1 to 1. Right, and for similar reasons, this green graph is 1 to 1. This red graph here is not 1 to 1. So maybe you noticed a pattern here. Whenever a graph is 1 to 1, notice how we could always draw a horizontal line, and that horizontal line will only touch the graph at one point. However, if we draw horizontal lines in these non-1 to 1 graphs, the horizontal lines will touch the graph more than once. Right? So here in green, the horizontal lines only touch the graph at one point. And here we could find horizontal lines that touch the graph at more than one point. This is called the horizontal line test. The horizontal line test is the following. If there is a horizontal line, if there exists a horizontal line you can draw on the graph that intersects or touches your graph more than once, touches the graph of a function more than once, then the function is not 1 to 1. On the other hand, if every horizontal line you draw, every horizontal line only touches the graph once, then it is 1 to 1. Right? So if we go back to these examples, we had a horizontal line that touched the graph more than once, so we conclude not 1 to 1. No matter what horizontal line we drew here, it will only touch the graph once, so it is 1 to 1. So this is the horizontal line test. Okay. Now the whole reason we brought up 1 to 1 functions is the following. So we have the following fact. If f is a 1 to 1 function, if f is 1 to 1, then there is an inverse of f. So f is 1 to 1, then it guarantees we can find an inverse of f. Right, so if a function is not 1 to 1, like here, we don't even need to bother swapping the x's and y's and trying to find an inverse, because if a function is not 1 to 1, the inverse will not exist. So we only try to find inverses for 1 to 1 formulas, right? And recall, we just find the inverses by swapping the x's or swapping the x's and y's. Okay, so now I'll give you some examples here. So x squared, right, looks like this. It's not 1 to 1, so there's no inverse. Let's say y equals x squared, no inverse to this formula. However, the graph y equals, I don't know, 1 over x, that has a graph that looks like this. Right, so no matter what horizontal line we draw here, the horizontal line will only touch the graph once. It says 1 to 1. And so since it's a 1 to 1, we could find the inverse by just swapping the x and the y. Right, so this is the inverse. Just swapped the x and the y. Okay. Do another example here. Let's say f of x equals 2x minus 3. So here I'm using f of x instead of a y, but they sort of mean the same thing. It's just a different symbol. Instead of a y, I'm using f of x. Now, let's find the inverse if it exists. And I'm going to introduce a new symbol here. Sometimes for the inverse, we do f to the minus 1. Now, we don't mean this as an exponent. It's just a superscript. So similar to subscripts that we've seen before, but we put the superscript on top here. So it's not an exponent. It's just a symbol to represent the inverse of f. Okay? Now, well, we know how to graph this, right? Intercept of -3, slope of 2, looks something like this. Clearly passes the horizontal line test, so this is 1 to 1, and therefore we can find the inverse just by swapping the x and the f values. So we did have f equals 2x minus 3. If we want to find the inverse, we just swap or invert the formula like this. So I use the inverse symbol now. I swapped the f with an x. I swapped the x with the f inverse symbol. Okay, and now we just solve for the f inverse symbol. So we could add 3 over and then divide the 2. So we have that the inverse of f equals x plus 3 divided by 2. Okay, now we could think of this, maybe you could rewrite it as 1/2 times x plus 3/2. So if we were to graph this, now the intercept is, I don't know, 1.5. Slope of, something like that. Okay, not a perfect picture, but there is a fact about the graphs. If I were to draw this graph better, you could notice the following fact. How do I want to word this? Say the graphs of f and f inverse are reflections about the line y equals x. So I'll draw a picture to demonstrate what this means. Here's the xy plane. In green, I'll do the line y equals x. So in this green dotted line is the line y equals x. Now if we have some one-to-one function that looks, I don't know, say it looks like this. Okay, so that's 1-to-1. Now the graph of its inverse will just be a reflection about this dotted line. So it's sort of like this dotted line, y equals x, is acting like the mirror, and we're going to just flip its reflection over to the other side. So I'll draw the inverse here in red. Oops, that's not red. Red. There's the inverse function. So f red is f inverse, and then black is f. And so we always have this happening. Whatever the function looks like, if it's 1-to-1 and its inverse exists, the inverse would just be the mirror image of the function, where this dotted line is acting like the mirror. So it's sort of a fact about inverse functions. You can use this to check your answers if you wish. Okay, what are some other facts about inverses? Well, there's another interesting property of inverses. So if f is a one-to-one function, f inverse is the inverse of f, then we get the following. If you plug the inverse into the original function, so if we plug the inverse into the function, everything will cancel out and you just get an x. But you have to be a little bit careful about the domain, so x has to be in the domain of the inverse. Okay, and then we could also plug the original function into the inverse and everything will cancel out except an x, but here x is in the domain of f. Okay, so let's return to that example we were just looking at. We looked at f equaled, was it 2x minus 3? The inverse was x plus 3 over 2. So we found the inverse. Let's also think about the domains here. Well, the domain of f, it's not very interesting in this case. The domain's all real numbers. Domain of the inverse is all real numbers. It's not a very interesting example. But anyways, if we plug the inverse into the original function, then we do 2 times x plus 3 over 2 minus 3. Well, notice these 2's cancel, you get x plus 3 minus 3. The 3's cancel, get x, just like we said would happen. Now sometimes you have to be careful about the domains, but in this case we don't have to be careful about the domains because the domains were really nice in this example. You could similarly do, f inverse, plug in f, then you just take this function, plug it in here. So we'd have 2x minus 3 plus 3 all divided by 2. 3's cancel, and then the 2's cancel, and then you get x. Let's look at another example, say, let's see if I could think of a interesting example of domains. Well, let's think about this function here. Let's do f of x equals x squared, but just for x greater than 0. So this is a function that looks like this, greater than or equal to 0, just like that. It's like if we cut the domain here to be x greater than 0, which forced the function to be 1-to-1, because now any horizontal line draw only touches the graph once. So this is 1-to-1, but you have to be careful. If we allowed for x to be negative, then the function would look like that, and it would not be 1-to-1 anymore. So the only reason this is 1-to-1 is because we're forcing the domain to be positive numbers here, right? So in this case, we have a 1-to-1 function, and then if you swap the inputs and outputs, we have x equals the inverse of f squared. Solve for the inverse, we get that. Okay? Now I'm only choosing the positive one here because if I chose the negative one, that would not make sense, right? If this was negative. But Since we were only picking x greater than or equal to 0, that would not make sense to pick the negative square root. Okay, now the domain here, x greater than or equal to 0, so we still get the same domain. Not too interesting, but we also can verify this property here. So if we plug the inverse into the original function, that's this, we get x. If we plug f into the inverse, we get square root of x squared, we get x. So those properties do in fact work. Now, let me give you a fact about the domain and ranges of inverse functions. So if we have the domain of f, it actually equals the range of the inverse function. And similarly, the domain of the inverse function is equal to the range of the original function. And that's not surprising because remember, an inverse function is just when you swap the x's and the y's, right? The y values are all the y values equals the range, all the x values equals the domain. So when you invert a function, what you are doing is swapping the domain with the range. So this is just true by definition, right? When we defined the inverse, it was swap all the x's with the y's, so therefore the domain is going to be swapped with the range. Okay. So it's another way you can verify you did something correct, or if you're ever asked a question to find the range of a function, you can use this fact to find the range of a function. If you want to find the range of some function, you could just look at the domain of the inverse, which is actually a lot easier to do. It's easier to find a domain than a range. Okay, let me think up some examples now. Let's look at this example here. Say we have a function 4 over x plus 9. And let's find the inverse if it exists. Okay? Well, remember, it only exists if f is 1 to 1, so we have to ask ourselves, is f 1 to 1? Okay, well, we could just use the definition of 1 to 1. Let me scroll back up to remind us. We had two ways of defining it. We could do this one. If f of a equals f of b, then a must equal b. So we could use that to determine if a function is 1 to 1. So if you don't know how to graph it, this is a good way to check. Well, let's say if f of a equals f of b, well then we get 4 over a plus 9 equals 4 over b plus 9. Right, this is f of a, this is f of b. So we're considering what will happen if f of a equals f of b. Well, let's just sort of cross multiply this out. We have 4 times b plus 9 equals 4 times a plus 9. And we could divide 4 from both sides, get rid of the 4's. minus 9 from both sides, get rid of the 9s. And we do in fact get that A equals B, so yes, this is 1 to 1. Right? If f of A equal to f of B, then A must equal B. So it is 1 to 1, and therefore we can find the inverse. So the inverse is when we swap the f and the x. So we start with f equals 4 over x plus 9, right? That was the original function. So for the inverse, we swap the inputs and the outputs. Okay. And now we just solve for the inverse. So I could cross multiply this out, and we get f inverse plus 9 equals 4 over x minus the 9 to the other side. F inverse equals 4 divided by x minus 9. Okay, let's look at the domain and range of the original function and the inverse function. The domain of the original function is we cannot plug in negative 9. We are not allowed to divide by 0, so we cannot plug in negative 9. The domain of the inverse is all the values except we cannot plug in 0 here. So if we plug in 0 there, you divide by 0, not allowed. Okay, and therefore, since we know the domain of the inverse, what this tells us is the range of the original function is all values except 0, right? Because as I mentioned earlier, the domain of the inverse is the range of the original. So since the domain of the inverse is all the values except 0, the range will be all the values except 0. You know, with the little side note, I used an x here because I was talking about domains, and used a y here because I was talking about range, but it's the same restriction here. We cannot equal 0, cannot equal 0. Okay, so this is one useful thing about inverse functions. It helps us find the range of the original function. Okay, cool. So let's try one last example here. Let's consider the function cubed root of 2x. And if you do not know how to graph it, to do the horizontal line test, you could check if it's 1 to 1 by doing this way. If f of a equals f of b, then cubed root of 2a will equal cubed root 2b. You can cube both sides. 2a equals 2b, divide by 2, a equals b. So yep, this is 1 to 1. We can in fact find an inverse. So since we have f equal cubed root 2x, if we invert this, that would give us x equals cubed root of 2 inverse f. And now we just solve for the inverse. We can cube both sides, and we get x cubed equals 2 times inverse f. Okay, so x cubed divided by 2 is inverse f. And then let's say we are not confident that we did this correct. We could check by plugging into, you know, f of f inverse. That would be, we take the inverse, plug it into the original function, and see if everything cancels except for an x. If we did that, the original function is this, and then we plug in the inverse. So notice these 2's cancel, and then the cube and the cube root cancel, so we get an x. So we can be pretty confident this is the inverse. If you want to check the other condition, plug in to the original function into the inverse. Cubes cancel out, and then the 2's cancel, and you get the x. Okay, cool. And with that, I will end this lesson. Thank you.